Hello everyone, Mehdi Mortazavi here with one example from the Clapeyron equation. So in this example, we are going to utilize the Clapeyron equation to estimate the value of enthalpy of vaporization for this refrigerant at a given temperature. So the enthalpy of vaporization is basically the HFG that we had in the tables. So the enthalpy of vaporization is H subscript Fg. And that is basically the difference between enthalpy in vapor phase and enthalpy in liquid phase. So HFG is in fact Hg minus Hf. Okay, so the temperature is given and we are asked to utilize the Clapeyron equation. So the Clapeyron equation, just to review that, says the change of pressure with respect to the change of temperature, dp dt, during the phase change or for saturation, let's say, is equal to HFG over temperature multiplied by specific volume, Fg. So this is the Clapeyron equation. Clapeyron equation. So what we are looking for in this problem is HFG. So this is our question mark. That means we should get the other properties from the table basically. So the temperature is given at 20 degrees C. What I'm going to do, I'm going to the correct table which has information for this refrigerant, and I am reading the pressure as well as the temperature for temperatures before and after 20 degrees C. So if you go to, depending on the textbook that you're using, but in the textbook that we use, if you go to table A11, so table A11 lists the property for saturated refrigerant R134A. This is exactly what we have in this problem. This column gives the temperature. In the problem statement, the temperature that was asked was 20 degrees C. So basically, the problem wants us to obtain HFG at this row at 20 degrees C. Okay? So basically, that HFG is already listed, but our plan is to obtain this number based on the Clapeyron equation and make a comparison with this number, which is 182.33. So the goal is I'm going to utilize information, the temperature and pressure at 18 degrees C as well as 22 degrees C. So my goal is to utilize the properties before 20 degrees C and after 20 degrees C. And what I'm going to use are basically the saturation pressure, because this column is Psat, that is the saturation pressure, as well as the temperature. So for 18 degrees C, this is the saturation pressure. For 22 degrees C, this is the saturation pressure. I'm going to utilize this. However, for 20 degrees C, I'm going to still use these two values because they are the specific volumes to obtain VFG. So this column is VG, which is the specific volume in vapor phase, in saturated vapor phase. This column is a specific volume in saturated liquid phase, and the difference between these two gives me VFG. So let's do that. Okay, so as I said, for the left-hand side, dp dt during saturation is going to be Psat at 22 degrees C minus Psat at 18 degrees C, the pressures after and before 20 degrees C. So basically our 20 degrees C is between these two values. And in the denominator, I will have temperature obviously at 22 degrees C minus temperature at 18 degrees C. So basically in the denominator, I could directly put 22 minus 18 because temperature at 22 degrees C is obviously 22 degrees C. Anyway, so this value is the saturation pressure of the refrigerant at 22 degrees C, which comes from table A11, again in the textbook that we are using, and value-wise, that pressure is 608.27 kPa. Okay, So this is the Psat at 22 degrees C for this refrigerant minus Psat at 18 degrees C, which is 537.52 kPa. And that is divided by 22 degrees C minus 18 degrees C. Now, regarding temperatures in thermodynamics, as long as we have the difference between the temperatures, you can easily use in degrees C. But if the temperature is showing up alone, that needs to be in Kelvin. For example, the temperature here in the right-hand side, that needs to be in Kelvin. So if you do the math, you will end up with dP over dt sat equal to 17.68, and obviously the unit is kPa over degree C, or you could say kPa over Kelvin, because again the difference doesn't really change. Now this is the left hand side of the Clapeyron equation. On the right hand side, this is unknown, but the temperature is 20 degrees C but converted into Kelvin, which is 293 Kelvin, and VFG is VG minus VF. So before plugging into the equation, let me obtain VFG, and that VFG is obtained at 20 degrees C. Okay, so VFG at 20 degrees C is VG minus VF, both of them at 20 degrees C. And again, these numbers are coming from table A17. So the value of VG from the table at 20 degrees C is 0.036.012 meter cube per kilogram. And so this is my VG, and VF from the same table at 20 degrees C is 0.00816 meter cube per kilogram. And at the end of the day, my VFG at 20 degrees C is equal to 0.03519 meter cube per kilogram. And at this time we have all the numbers that we need, so let's plug in to this equation. So on the left hand side we have, and just to make it clear, so if this is the red star gives us 17.68 kPa over degree C is equal to HFG that we are looking for over temperature, but once again this temperature needs to be in Kelvin, so 20 degrees C converted to the Kelvin will be 293 Kelvin multiplied by VFG, and VFG being this value 0.03519. Okay, so if you do the math, you will end up with HFG equal to 182.32 kilojoule per kilogram. So this is the HFG that we obtained from the Clapeyron equation. So this value comes from the Clapeyron equation. So the question says compare it with the tabulated value. So basically that means compare it with the value we have in the table. So the tabulated value from table A11 for 20 degrees C is HFG equal to 182.33 kilojoule per kilogram. Okay, so this is the HFG coming from the table. So this is table A11 for this textbook. So once again, this is the textbook that I'm using, edition 8, but I'm sure that the tables are pretty much the same for different editions. So this is the tabulated value, and this is the one that we obtained from the Clapeyron equation. See how close they are.